York, metropolis of the modern world, symbolized by its famous man-made skyline, a skyline made up of buildings of steel founded on solid bedrock, buildings towering hundreds of feet, some more than 1,000 feet above ground level. Prominent in the famous skyline are a number of great steel bridges. Among them are the Brooklyn Bridge, the Triborough and Hellgate Bridges, the Henry Hudson Bridge, and the George Washington Bridge, all vital to New York's transportation system. In this city of thousands of towering steel structures are the nerve centers of worldwide commerce, communications, finance, and industry, headquarter units of organizations of national and international importance. In the midst of this bigness, this strength, this importance, is the setting for a new group of buildings to house the headquarters of the United Nations. A group of buildings that have been called the most important buildings in the world. The site for these buildings, an area of 17 acres, was acquired through a gift to the United Nations. It extends from 42nd to 48th Street and from First Avenue to the East River. Members of an international board of architectural and design consultants, headed by Wallace K. Harrison, designer of Rockefeller Center, pool their talents to create the plan for the home of the United Nations. Many strikingly original ideas for bold and unique structures were presented. From some 30 basic schemes, they reached unanimous agreement on an overall design for the new buildings. The largest building, the Secretariat, was scheduled to be constructed first. This unique towering structure, 503 feet high, 284 feet long, and only 72 feet wide, presented unusual problems to the engineers who prepared general plans for the structural steelwork. It is doubtful whether these unusual problems could have been solved but for the great strength and adaptability of steel construction. While planning proceeded, clearing the old buildings from the site was in progress. Walls came tumbling down as steel wrecking equipment hammered and smashed at the structures, and steam shovels gnawed away at the rubble. The area, extending over 6 city blocks, was stripped clean, made ready for the building contractors. By this time, the United Nations had already entered into a contract with American Bridge Company to fabricate and erect the structural steel framework. They had also contracted with a combine of 4 of the largest construction companies in the eastern United States to handle all other phases of the project. To prepare footings for each of the steel columns, pneumatic tools dug down to bedrock, as deep as 50 feet in some places. Forms were then built for the footings. They varied in size, the top of the largest being 12 feet square. Thousands of cubic yards of concrete were poured into the deep forms in which steel reinforcing rods had previously been set. As much as 200 cubic yards went into each of the larger footings. When all these footings were their level and alignment, steel grillages weighing from 4 to 12 tons were set into position on these reinforced concrete footings. The grillages used in this building are made of I-beams. Each grillage serves to spread the concentrated load borne by the steel column over the entire area of its footing. The setting of the grillages in the construction of a building is a very important operation. For if the building is to stand true, the grillages must be in perfect level and alignment. Center lines aided the engineers in properly positioning the grillages. The engineers made a final check to be sure that the columns would stand exactly plumb. Finally, concrete was poured to embed the grillages firmly into the footings, thus completing the column foundations. While the site and foundations were being prepared, American Bridge Company engineers made detailed drawings of every piece of steel for the building. In the meantime, steel for the structural sections was being made in the great furnaces of United States Steel. Out of the open hearths poured the molten steel, rigidly controlled to specifications. Tests were made throughout every stage of the steel making in line with standard practice. Hundreds and hundreds of ingots were cast to make the structural steel for this building. After the ingots had cooled, the molds were stripped from them, and they then went to the rolling mill. Scale breaker rolls received the ingots and prepared them for the shaping rolls. Back and forth the ingots passed between the rolls, slowly taking shape. They emerged from the finishing stands, some as long as 150 feet, to be cut to length as required. This strong, sturdy steel, made and tested to specifications, will do the job planned by the engineers. Its quality and strength are built in. They do not depend on the human element in field work. From the rolling mills, the steel for the Secretariat building was shipped to the fabricating plant of American Bridge Company at Ambridge, Pennsylvania. The receiving yard temporarily stored the 14,000 tons of steel. Heavy steel sections were required for the fabrication of the columns, the vertical members of the structure. Rivet holes were drilled in the web of each heavy section by a vertical multiple drill. Then cover plates were added to the sections to provide the necessary strength to carry the heavy loads. Now the assemblies began to take the shape of column sections. The parts were tack welded to hold them together temporarily. Next, the ends of the column section assemblies were milled to reduce them to exact length, and at the same time, to provide smooth surfaces where one section rests on another. Rivet holes were drilled in the flanges by a horizontal multiple drill. The number of rivet holes and their position were indicated on the shop drawing. Holes were drilled in the column section assemblies rather than punched because of the great thickness of the steel. Holes were punched in the beams, the horizontal members for this building, where the material permitted this operation. Beam connections were accurately fitted to the column section assemblies and secured by temporary bolts until they could be riveted. The final operation in the fabrication of column sections was done by the riveter. Under its tremendous pressure, the rivets drew the component parts together perfectly. The column sections, which were to rest on the foundations, were fitted with heavy wing plates to distribute the load evenly over the foundations. The structural steel was painted for permanent protection, except for the accurately milled ends, which were coated with a compound of white lead and tallow. Each column and beam was numbered to show its exact position in the framework of the building. Completely fabricated, the steel was loaded for shipment to a temporary storage yard near the site. Railroad cars carrying the heavy column sections were brought across the Hudson River to the west side of New York on lighters. There, the steel was transferred to trailer trucks to be transported through the busy city streets to the site. Movement of the steel to the site, exactly on schedule and as required for erection, was an example of perfect planning and coordination of designing, steel making, fabricating and shipping operations. The first column sections to be erected were moved into position by a crawler crane. These lower column sections were then erected on their respective foundations. The largest were designed to carry a direct load of more than 3,600 tons. Yet the steel itself, the strongest building material in relation to its volume, occupies an area of only 27 by 36 inches. The use of steel construction permits a saving of many square feet of valuable floor space. When one sees the column sections set upon their foundations, it becomes evident that the wing plates distribute the weight and load of each complete 40-story column over the area of its foundation. The tremendous downward thrust of those 40 stories above will hold the column rigidly against the foundation. The bolts merely connect the wing plates to the location lugs of the grillage. They carry no load except during erection. The lower parts of the column sections are protected by a special waterproof coating. The first of the 3 guy derricks used in erecting this building is now in operation, and up goes a 33-ton column section, the heaviest of them all. The hoist operator raises the steel. Then the raising gang, using the bull stick, swings the derrick boom and its load into position. These column sections, with their bases 3 stories below ground floor level, are the lower members of the 537-foot steel columns which will serve as the vertical framing of the building. The beams, which make up the horizontal framing, are moved by lighter from the storage yards, arriving as needed at the East River piers near the building site. These beams will support the reinforced concrete floors. The new building begins to take form, with every piece of steel going into the exact place in the framework for which it was designed and fabricated. Following the usual practice in steel building construction, the building is erected in tiers. That is, 2 floors at a time, or the length of the column sections. And so construction proceeded according to schedule, tier by tier. Steel erection reached the 14th floor on the 40th working day. As soon as a tier is erected, planks are brought up and laid as a temporary floor on the beams to serve as a safe base of operations for the erection of the next tier. 2 complete sets of planks are used, so that even when one floor is being laid, there is always another temporary floor 2 stories below the workmen for their protection and that of other trades working below. The next step is to raise the guy derricks to the top of the tier just completed. Guy derricks can lift themselves from tier to tier as the building rises. This feature makes them extremely practical in the erection of tall buildings. First, the boom is placed in a temporary base called the jumping shoe. Then it is temporarily guyed in a vertical position. It then serves to raise the mast to the tier above. There the mast is secured to its relocated base and plumbed up. The mast then raises its boom to the new level. When reassembling is completed and the wire rope guy lines are again in place, the derrick is ready to resume work. In the actual operation, members of the derrick gang make adjustments at the top of the boom and mast preparatory to the raising. The boom is removed from the mast and is placed on the jumping shoe. The signal is given, and up comes the mast. When it reaches the new level, its supporting base is moved into position. Next, the boom is raised and pinned into position. The derrick is now ready to raise steel for the next tier. These column sections, designed for the upper floors, are somewhat lighter than the lower column sections. Double wire rope slings are used as a safety precaution. With the hoisting engines operating on the ground and the derricks atop the frame, visual signals are not possible. The bellman alerts the hoist operator by putting tension on the signal rope and then gives bell signals by quick tugs on the rope. But the signaling works out perfectly because of the precise cooperation of the bellman in each raising gang and the hoist operator. Teamwork is a vital factor in the work of the raising gang. Each gang, in addition to the hoist operator and bellman, is composed of 2 floormen, 2 connectors, a bull stick man, a tagline man, and a foreman. A pin is inserted in the splice plate holes, and the column section is raised by the derrick. Column section after column section goes straight to its place in the framework, guided by the able and experienced men of the raising gangs. With a boom serving a 75-foot radius, the men on the bull stick can swing the load through a wide area. Each column section is set into position between the splice plates of the lower section, and drift pins are driven to line up the sections accurately. The column sections are secured with temporary bolts until the splices can be permanently riveted. Then the pin is pulled and the derrick is ready for another hoisting operation. Safety on the job is stressed at regular safety meetings, usually at the beginning of the shift. The men are equipped with helmets called skull guards and other safety equipment. A booklet of safety regulations is provided every worker. Posters emphasizing safe working practices are an important part of the safety program. On the 58th working day, construction reaches the 20th floor on schedule, exactly as planned. Tier after tier, the steel rises, a skeleton in the sky. At this stage of operations, the structural steel is being erected at the rate of 1 tier or 2 floors in approximately 6 working days, or about 48 working hours. Yes, it looks easy, but that's because of the accurate planning of the engineers and the precise teamwork of the skilled steel erectors. The steel itself speeds the work, for no time is lost in cutting or fitting on the job, and it is ready to carry its weight as soon as bolted and riveted into place. Nothing is left to chance on a steel erection job. The number and location of every beam and column section is shown clearly on the blueprints, and these are referred to at every step of the operation. The beams have all been laid out on the floor so that the foreman can easily locate the next to be erected. He finds it addressed like a piece of mail, with markings indicating its exact position in the structure, along with a number of other symbols which have brought it to its present location. Up goes the beam to its designated place, guided into position by the skilled connectors. The openings in the web of the beams offer passage of air conditioning ducts and other utility services. Running these through the beams saves valuable space between floors. Agility and brawn are second nature to these experienced workers. They are accustomed to working at dizzy heights. They get about as conditions dictate. They get places fast. The derricks hoist the steel, but it takes experienced men and alert cooperation between the bellman and the hoist operator and the other members of the raising gang to raise and fit the beams between the connections. And there's a lot of steel to be fitted into this framework, over 10,000 structural pieces. The larger members, extending from column to column, are known as header beams. Rigidity of the framework and further support for the floors are provided by placing intermediate beams between the header beams. At the ends of the building, beams known as spandrel beams are placed to support marble curtain walls. The structural steel erectors are sure-footed and unafraid, quite at home up there, for many of them have been doing this work for 20 years, 30 years, and even longer. They're not young daredevils. Their average age is 45. They're family men. In fact, 6 of them are grandfathers. More than one son is following in his father's footsteps. Over 20 nationalities are represented in the American bridge crew of 83 men working as a team to erect the steel in this building. Construction is moving right along on schedule, reaching the 26th floor on the 70th working day. Construction could have proceeded at a faster rate had the schedule called for it. Beams are fastened to column sections by means of 3 brackets. The vertical one is the shear connection, which carries the vertical load. The upper and lower ones are wind brackets. Steel, the most compact building material, permits the design of simple connections to resist the wind pressures exerted on the great exposed areas of this wide, thin building. Header beams are bolted temporarily, just like the column sections, until they can be permanently riveted. Beam-to-beam connections are permanently bolted rather than riveted, as the stresses at these points are comparatively minor. Here's a good job for a bow-legged cowboy. As erection progresses, each tier is plumbed before riveting so that the column sections are exactly vertical. The weighted plumb line must be parallel to the column section from top to bottom. By manipulating the turnbuckles on the wire rope plumbing lines, the column sections are adjusted until the rules show that they're exactly plumb. From a fixed point on the ground, the building is also checked every day after working hours, when there is no vibration of the structure. Steel construction permits visual inspection of the frame during and after erection. After each tier was plumbed up, it was ready for riveting. 8 riveting crews worked closely behind the raising gangs. Each riveting crew is made up of 4 men: heater, a sticker, a bucker-up, and a riveter. Apprentices keep the heater supplied with rivets of the correct size for the section being riveted, exerting pressure on the rivet head while the hammer forms the other head. A manual type of plucking up tool, the offhand dolly, is required in certain locations. The web of the beam is riveted to the shear connection on the column section. The flanges of the beam are riveted to the column section wind brackets. $170,000 rivets were put into the frame in the course of erection, not including the hundreds of thousands which were driven in the fabricating plant. Rigid steel construction of this type provides the most effective resistance to shock, even to tornadoes and earthquakes. Every rivet is tested and faulty ones are replaced. Properly driven rivets completely fill the rivet holes. Riveting of column section to column section is called splicing. Some of the rivets used are as large as 1¼ inches in diameter. Splice plates of a lower column section overlap the base of the column section above. When these are joined by rivets, the column sections form a continuous load-sustaining steel column from foundation to the top of the building. On the 82nd working day, the 32nd floor was reached, and again, just as planned. As the days pass, the dreams of the architects and engineers begin to take shape. A steel giant standing solidly on bedrock, a noteworthy addition to the famous and dramatic Manhattan skyline. As the framework grows, other building trades follow the steel erectors floor by floor. Air conditioning equipment arrives. Large steel water tanks go up and are set right into the framework of the building. Wire rope is seen everywhere on this job, in hoist lines, guy lines, plumbing lines. 20 miles of pedigreed wire rope elevator cable will serve the 22 elevators in this building. Talk about beehives, the building is a study in activity. Silhouetted against the sky, the steel skeleton teems with the men of various building trades, significant of the speed of construction which only steel can provide. The work of many building trades may progress simultaneously at various levels in the building. Acres of wire fabric are rolled out over the wooden forms on which the concrete floors will be poured. Steel reinforcing rods, in combination with the wire fabric, provide necessary strength for the concrete floors. And there'll be acres of metal lath and ceilings and partitions, too. Yes, steel is everywhere. Hundreds of tons of pipe, for instance. The electrical system alone calls for steel conduit carrying 500 miles of wire and cable. There are 11,000 electrical outlets. Reinforced concrete floor construction closely follows steel erection. Steel permits a wide variety of floor construction, light or heavy. On its narrow ends, the towering structure is faced with marble, the weight of which is carried by the spandrel beams on each floor level. This is the only building with marble facades of such a height and with the extreme accuracy of the steel framework, only 1/2 inch out of plumb in its 40-story height, makes it possible for the masons to set the marble curtain wall in a true vertical plane. Slim, true, and beautiful is this mighty building, a sheer 500-foot shaft reaching toward the clouds. As the metal window sash is set into the steel structure, the unique beauty of the building transforms the architect's drawings to reality. 5,400 windows make this building one of the best lighted structures ever built. With 6 acres of glass in the endless windows facing to the east and to the west, it will look like a gigantic glass house against the sky. Tier after tier, the building climbs until it attains a height of 40 stories. The last beam is fitted into place. And from the furnace, the last rivets fly like tracer bullets to the riveters. For the American Bridge Company men, the job is done. And now, the 40-story steel framework, begun in April, is completed in October in 97 working days. Topping out at the end of the job is an important event to the men who have worked together through these months. The blue and white flag of the United Nations, with its olive branch symbol of peace, now flies in the breeze. The President of the United States and representatives from all lands join with United Nations delegates in dedicating their new capital. The world listened in as the ceremonies were broadcast in 26 languages. President Truman said, "These are the most important buildings in the world, for they are the center of man's hope for peace and a better life. We must make our devotion to the ideals of the Charter as strong as the steel in this building." Trigvalee, Secretary General of the United Nations, laid the cornerstone, a 4-ton block of granite bearing the inscription, United Nations, in English, French, Chinese, Russian, and Spanish. And so, the first and largest structure of the home of the United Nations took its place in the dramatic skyline of the City of Steel. Not just a great and beautiful skyscraper, but a structure which symbolizes in steel and masonry the hope for peace and happiness for all the peoples and all the nations of the world.